In this lesson, we'll learn about sets, which is something that we'll use a lot in our study of abstract algebra. Now, set can be thought of as a collection of things called elements. So here's our first example, the set of integers, which we'll denote by the script letter z. So z, or the set of integers, contain the positive counting numbers 1, 2, 3, 4, 5, and so on, the 0 element, and all of the negatives, negative 1, negative 2, negative 3, negative 4, and so on. Now, when we think about sets, we often talk about which numbers or elements are in the set of integers, say 3 is in the set of integers, versus which aren't in the set z. For instance, 2/5 is not in set z. And because we talk about this idea of which elements are in this set versus not, we talk about that often, and so we have a shorthand for it. And so here's our notation. We write 3 with this funny little looking symbol, and z. This literally translates to 3 is an element of z. That's what we see right here. 3 is an element of z. Whereas 2/5 is not an element of z. So this slash through the is an element of symbol makes it not an element of z. So kind of like slash through the equal sign makes it not equal to. So this can be read as 2/5 is not an element of z. So now we have the set z. We can also talk about its subsets. And so here's our first example of a subset. So we have a subset of z, and let's give it a name. We'll call that subset A, and it contains the following elements: 3, 5, 7, 17, 19. And so here's our first question, and please pause the video and see what you can do. Write down all of the elements of this subset A and answer how many elements are there in this subset A. Now let's write down the elements of our subset A, which really entails trying to figure out what this ... represents. And so here we go. Set A contains, well, we know it has 3, 5, 7. What's next? Well, you might perhaps think it's 9, but we're going to skip 9 and go to 11, and then 13. And you might think it's 15, but let's skip 15 and end up with 17 and 19. And so it's a bit of a trick question. Perhaps it's natural to think that I was thinking of all the odd integers between 3 and 19, but in fact I was thinking of primes between 3 and 19. Now, this somewhat of a trick question was meant to illustrate that a notation such as ... can be misleading or vague at best. And that's why it's important oftentimes to, rather than listing the elements of a set or a subset, to describe that set using the properties that its elements satisfy. Now you might say, well, why not just list them all? Well, in this case, sure, there are only 7 elements, but what if I wanted to have a subset that contained all the primes between, say, 3 and 1000? I don't want to go through the trouble of listing them all, but I would like to be able to describe that subset using that property. And so because we do this sort of thing often in abstract algebra and mathematics in general, here's a notation to describe our set A. So here it is, and it has multiple parts, so let me go through it one by one. First we have A, that's going to be the name of our set, or in this case a subset of the integers, equals. Now this first part, n is an element of z, that tells us where the elements of our subset comes from. In particular, the elements come from the integers, and that's why all of its elements are integers. And then we have this vertical line that reads such that, and please be careful, this notation such that as a vertical line is used inside the set notation only. And so if you're writing a proof and you want to write such that, please write out the phrase such that rather than using a vertical line. But within the set notation, this is the standard way to do it. And then we write down the property that's satisfied by the elements of our set. And so this is the full description of our subset A. And again, much more precise than using the notation like dot, dot, dot. And now, please pause the video and work on day 2 classwork. And afterwards, we'll discuss some of the problems and ideas that arise. In the classwork, we considered the set 3z, which is the set of multiples of 3. So it contains 3, 6, 9, 12, etc., all the negatives, as well as 0, because 0 is 3 times 0. And we were asked to prove the following. If m and n are elements of 3z, then their sum, m plus n, is also an element of 3z. Now, when that happens, we say that the set 3z is closed under addition. And closure is a concept that we'll study a lot in abstract algebra. And so here's our very first closure proof. And before we get into the proof of it, here's a visual of what's going on. So imagine this bubble shape representing the set 3z. And what are we trying to prove? Well, we're trying to prove that if, say, m and n are elements of this set, they're inside the set, then when you add them, let's represent it this way. Here's our m plus n. Then the sum m plus n is still in 3z. So I think of this as, what happens in 3z stays in 3z, at least when you're adding the elements. And so let's now write down this proof. We will first identify the hypothesis and the conclusion right there. So we already know what our first line and the last line of our proof looks like. Here they are. We're assuming the hypothesis, m and n are elements of 3z. And our very last line, our conclusion, is that m plus n is an element of 3z. Now, in the classwork, you actually analyzed the following proof, which contains a subtle logical error right here. And so let's go ahead and analyze that. Well, first, we know that m is an element of 3z, so we can write it as 3 times k, where k is an integer. And likewise, n is 3j, where j is an integer. And I also remark that here we can't say 3k and 3k for both m and n, because that would imply that m and n represent the same integer, but they don't have to. So let's use k and j here. Now the next line, this is where we have that subtle error, because if we were to reason this through, the order of steps would be m plus n. Well, then we substitute to get 3k plus 3j. And then we would factor out the 3 and get 3 times an integer, namely k plus j. And so it should read as m plus n equals 3k plus 3j equals, factor out the 3 times k plus j. And so what we really need to do is to swap these two expressions. And so I'll indicate it like this. These need to be swapped to more clearly reflect our thinking, which once again is that m plus n after substitution equals 3k plus 3j. Factor out the 3 to say 3 times k plus j, which is finally an element of 3z, because it's 3 times an integer, namely k plus j. And therefore we can conclude that m plus n is an element of 3z. And so that was the subtle logical error we saw in the classwork. Now in the classwork, we also looked at this set C, which contains elements of z such that n is an element of 2z and n is also an element of 3z. And so this contains the set of multiples of both 2 and 3. So for instance, 18 would be in set C because 18 is a multiple of 2, 2 times 9, and also a multiple of 3, 3 times 6. And so the claim that you might have made, or conjecture that you might have made, is that this set C is the same as the set 6z. So those two sets are equal. And in fact, that's true. And now I like to ask the question, well, how do we prove it? More generally, how do we prove that two sets are equal? And that's going to be the focus of our discussion here. And so here is a general proof know-how. If we want to show that two sets, let's call them generically set S and set T, if we want to show that those two sets are equal, meaning they contain the exact same elements, then we have to prove two things. Namely, S is a subset of T. That symbol right there means subset of. And also T is a subset of S. So we have to show two things. Now this is perhaps in calculus. You might have studied if you want to show that two real numbers are equal, x and y, then you might show that x is less than or equal to y, and y is less than or equal to x, and therefore x must be equal to y. This is the set analog, if you will, of that concept. And so let's say we want to show, for instance, that S is a subset of T. How do we go about that? Well, here's the visual. If we want to show that S is a subset of T, here's S, here's T. We want to show that S is contained entirely within set T. So what are the steps involved? Well, to say that S is a subset of T means every element of S must also be an element of T. Now, how do we write that as an implication? We like to write this as an implication because we know how to prove implications. Well, let's think. Imagine an element N that's inside S. Now, if every element of S is an element of T, then that element N, which is inside S, must also be an element of T as well. And so written as an implication, every element of S is an element of T is the same as if N is an element of S, then N is an element of T. And that's what we want to prove. And so how do we do that? Well, now we have our usual way of proving an implication. We assume the hypothesis and we prove the conclusion. And so what we do, if we want to show that S is an element of T, what do? Well, we assume N is an element of S, and then we show that N is an element of T. That's how we typically show that S is a subset of T. Now, if we want to show that S and T are actually equal, well, we have to do both directions, namely S is a subset of T and T is a subset of S. Now let's apply this proof know-how to prove that sets C and 6Z are equal. Now remember, that would entail showing that C is a subset of 6Z and also 6Z is a subset of C. So we would have to write two separate proofs. Now for now, we're going to focus on one of them. 6Z is a subset of C, depicted by the visual here. 6Z sits inside C. And I'll leave the other direction, namely C is a subset of 6Z, for you as homework. And just as a reminder, C is the subset of Z that contains all the multiples, all the integers that are multiples of both 2 and 3. And so let's start writing the proof of 6Z is a subset of C. Now, the first thing we'll do is translate that to an implication, namely, if N is an element of 6Z, then N is an element of C. And we can see that by the visual here. If we want to show that 6Z is a subset of C, we take any arbitrary element inside 6Z, and we have to show that it's also inside or contained in C. And because we identified the hypothesis and the conclusion, we already have our first and last lines of the proof as usual. And so let's go ahead and fill in the rest. And we know that N is an element of 6Z, so we can say then N must be a multiple of 6. In other words, N is equal to 6K for some integer K. Now, looking ahead gives us a clue on how to proceed. We have to eventually show that N is an element of C, which means we have to show that N is a multiple of 2 and a multiple of 3. Now let's take advantage of the fact that N is a multiple of 6. And so if N is a multiple of 6, first I'll show that we can write it as a multiple of 2 by rewriting 6K as 2 times 3K, where 3K is an integer. And so we just rewrote N as 2 times another integer, namely 3K, and therefore we can say that N is an element of 2Z. And similarly, we can rewrite n as a multiple of 3 by saying 3 times 2k, where 2k is still an integer. And so we can say that n is a multiple of 3, or an element of 3z. So we just showed that n is an element of 2z and also an element of 3z, and therefore we can conclude that n is an element of C. And so that concludes the proof of showing that 6z is a subset of C. And remember that if we want to show that 6z is actually equal to C, we also have to show the other containment, namely C is a subset of 6c. But I'll leave that up to you. And that's the end of this proof, and also the end of this lesson. And I will see you next time.